Dream to become the next Sir Isaac Newton or Albert Einstein? Learn from the master. Refath Bari. Watch his videos to achieve your dream.
Today we're going to be continuing our discussion on the 4 fundamental subspaces. And as a matter of fact, as a result, we don't have any do now. Just kidding, we do. What is our do now going to be? Find.
Or throwing projectiles at me. Mr. Rodriguez.
Identify the name and notation of all.
I almost was thinking to do it right thing.
Of all 4 fundamental what?
All 4 fundamental, like your fundamental law, fundamental
Subspaces?
subspaces. It's like a fundamental law of algebra.
Yeah. Okay. So I'll give the audience a few seconds and good luck.
We've only got to the central law just now at the 72nd freaking lecture.
Yes. So
That is
anybody want to guess what they are? Who remembers what they are?
Not me.
Alex, do you remember?
For subspace?
Yeah.
No. I don't.
Okay.
Sorry.
Of course.
So
Everybody doesn't remember. Nobody remembers.
what are the 2 things that every matrix has? Every matrix has this and that. What are they?
Rows and columns.
Okay, so then it would make sense that 2 of the fundamental subspaces are the column space and what space?
Row.
The row space. Okay. And we learned 2 more spaces last lecture. Do you remember what they are? 2 more spaces?
No.
Okay. Let me write them down. They're the null space, and the left null space. Left null space. Okay, but we're not even done. So Alex, why don't you come up here and write the notation for all 4 of these spaces?
I don't know.
Give it a shot. We saw it yesterday.
You sure?
Yeah. It's not that bad. Do you want a hint?
No, I'll do that.
Okay.
Notation for column space, you said?
Yeah, all 4 if you can, or just any of them that you think you can. Right?
Notation for column space, row space. Blackout. Sorry.
Oh, okay.
Completely blackout.
Well, column space, so it starts with a C, so we're just gonna put C.
Okay.
Row starts with R, so we'll just
Okay.
put R. Null space starts with N, we'll just put N. Left null space starts with L, we'll just put L.
That's it? Oh, it's not that bad.
Yeah, and it acts like a function, so you just put of A. So column space of A, row space of A, null space of A, left null space of A. Okay, so hopefully that makes sense. Okay, so now we're gonna move on to a lesson where we're gonna identify some of these spaces. Actually, what are we gonna identify today? Let's identify the column space and the null space. Okay, yesterday we did the row space and the null space. Today we're going to be doing an example of identifying the column space and a null space of a matrix. Okay, so let me erase what's up on the board. Let's erase all of this. Okay, so 1 1 0 0. So does anyone know what this is?
Oh yeah. This is a 2x2 matrix.
It's a matrix, right? And okay, so we can call this matrix A, right?
Yeah.
Okay. So remember in the do now we were talking about the 4 subspaces of a matrix,
Right.
right? So today we're going to be focusing on the column and null space. So first, let's look at the column space. Okay. What is the most important equation in linear algebra? The most important equation in linear algebra.
Ax equal to b.
Okay, Ax equals b. Ax equals b, right?
Yeah.
Okay. But how do you know Ax equals b has a solution? Is there, for example, how do you know if a graph is a function? How do you know that this is a function?
If it is if it's satisfy all the requirements, like whether it's passed the horizontal test, vertical
Yeah.
test.
So if it has some test, you know that it's a function.
Right.
Just like that, there are some tests that we can do on Ax equals b.
Right.
And we can stick it in the wall and see if it moves.
Right.
Okay.
Sure.
So does it move?
Does it move?
Yeah.
What do you mean? Can you give me some hint?
So how would you test if Ax equals b has a solution?
Oh, right hand side equal to left hand side.
Okay, good idea. But the better way is to think of the matrix as a linear transformation,
Okay.
right?
So
Every matrix is what?
every matrix is
A
a
linear
linear transformation.
So if I
with rows and columns.
with rows and columns. So if I start with my regular xy plane, and of course we're gonna start off with a horrible xy plane. So if I have x and y like that, what are my 2 unit basis vectors? Anyone know? Unit vectors, come on, basis vectors.
Oh, unit vector.
I had
Oh, I had j hat, k hat.
J hat. We were in R2, so no K hat.
Not k hat. Okay.
Okay. And I'm gonna take this matrix
Okay.
and apply it to this coordinate plane. Okay? Gonna take this matrix and apply it to this coordinate plane. So what am I gonna get? Who wants to wager a guess? After I take this matrix and apply it to the coordinate plane, what is gonna be the result? Yes, Alex? Raise your hand. What do you wanna say?
Say what?
So after I apply the matrix to the coordinate plane, what's gonna be the transformation look like? Well, look at the columns. This is the new I hat, right?
Mm-hmm.
This is the new what?
The new j hat.
J hat. So what will the transformation look like?
Transformation.
What was the old I hat?
Old I hat is something comma 0.
1, 0, right? 1
One
to
comma.
x, 0
Yeah,
to
1
y.
comma 0. 0 comma 1.
0, 1. And then what are the new I hat and J hat?
1 0.
And J hat?
1 0.
So what is that?
So I hat will not change, but j hat will lie on the I hat.
Okay, so what does that look like?
That line just.
It's just a line. It's just a line.
Oh.
So the whole 2D. So this is a very amazing.
So
thing.
2D collapse to 1D.
1D. We say this transformation takes 2 dimensions to 1 dimensions.
Oh.
Okay.
Or 2D collapse to 1D.
Yeah. So imagine you're a human being
Right.
and some giant stepped on your face. You would become a pancake on the floor.
Right.
You would become 1 dimensional.
Yeah,
Right.
something like that, I guess.
So you would become from a human to a pancake.
from 3D to 1D.
And that's basically what happens in a car crash. The victim becomes a pancake. So the victim gets transformed from R2 to R1. So you can.
What about someone cut the rope of the elevator?
I like that. Boom, you die, and you become 1D.
Yeah,
You
it's kind of a fun experience.
A splatter on the floor.
Yeah.
So,
Imagine you can become like a pancake.
In that case, you actually go from fully 3D to just like a garbage on the floor, R1. Kind of sad, but that's the.
What part is the sad part? I don't see any sad part there.
Oh God. I'm sure neither do any of our viewers. Okay, they don't understand what's going on. So, sorry for that. So I hat is just gonna be 1 0. J hat is gonna be 1 0. They're gonna lie on top of each other. Okay. Okay, good. But back to our original question, which is how do you test if AX equals B has a solution? Well, what do is any B for which there exists an X is gonna lie on this line. So all of the B's that do have a solution are gonna lie on this line. Okay? Go out of this line and boom, there will exist no X, no solution. Okay? So that's gonna be the column space. So how do we formalize this idea? How do we formalize this idea? Any ideas? How can I mathematically express what I just said? How can I mathematically express the column space?
Express what?
The column space. Hint? Need a hint?
CA.
Okay, so we can start off with CA. Okay, so far so good. CA, okay. But CA is what? What is CA equal to? How can we...
R1.
Okay, yes, okay, well, CA is an element of R1. But what is CA? That's good. Yeah, it's an element of R1 because you can see it's being crushed to the number line. But what is it equal to? Should I give a hint?
Yeah.
Right? Basically, you're looking for all the B's, such that AX equals B.
Uh,
So what is this saying? It looks like simple, but this is saying a lot. This is saying the column space of A. What is the column? What even is the column space? What does that mean?
one of the
One of the subspaces. But what is a subspace? A subspace is just, remember, a subspace is just a vector space that satisfies three properties.
right.
What are the three properties that every vector subspace follows? Right? The zero is an element of the subspace. Okay. What else? The subspace is closed under addition, right?
Close under scalar multiplication.
And closed under scalar multiplication, right? That's what a subspace is.
Zero in what?
Zero is an element of the subspace. Every element has to have zero. So zero is like
Zero is the hero.
oh yeah. So every subspace has to satisfy these three properties, and the column space satisfies all three of these properties, and so we call it a column subspace. It's just nice to have, right? Because how many times, if you're taking a linear algebra course in college or in high school or elementary school, even better pre-kindergarten, then the first thing you're gonna learn is how to solve AX equals B. We all know we used to do it with Gaussian elimination, right? But there are some B you cannot solve for. There is some B in the world that there is no X for. How do we know what those B are? Those B are the B's that exist in the column space, okay? So if this idea is uncomfortable to you, that's great. I've made you uncomfortable and that is my goal. But as you continue to deal with the idea, we're just getting started.
Okay.
As you continue to deal with the idea, it'll hopefully become more clear. Okay, so let's formalize this more. Okay, if I multiply a matrix by a vector, what am I gonna get? how can I expand this notation? 8 times x, how can I expand that? Any volunteers? Okay. Yeah, so good idea. So it's actually going to be a1 x1, right, plus a2 x2 all the way to an xn. Okay, so there you go. We've just expanded out a times x. Hopefully that makes sense. What did I just do? Well, let me show you. What I just did was I took a regular matrix m by n, m rows and n columns, and I multiplied it with a vector that of course has to have m rows. So what do I do by that? Well, say
Okay. I think this is the 4th of July again.
I think the audience got a little bit too excited, so please calm down, okay? We don't want to start fireworks here. Okay. Okay, so back to my original question, which I have to rush to close the fireworks. So we are currently trying to express the column space of a matrix. Okay, so we are at this stage. How can I read this using my mouth? Well, I can say the column subspace of the matrix A is equal to all vectors B such that AX equals B. Okay, and I know the live viewers can't see my face, but that's perfectly fine as long as you see what I'm writing. I can remain faceless. Now, AX, how can I multiply or how can I expand a matrix times a vector? Who knows the answer? Sorry. Who has an idea? Any ideas? What is A times X? What is a matrix times a vector? How do I express that? Well, maybe I can give a hint. A is a matrix, right? So a matrix is m by n, right?
Yeah.
And
X is a vector.
X is a vector, and
Vector is
x1, x2, all the way to xn.
yeah, is equal to
And yeah, and A has m columns, right? Sorry, m yeah, whatever. Okay, A2 all the way to an. Right? That hopefully that makes sense.
it does.
That makes sense so far, right?
Yeah.
So A has n columns, the vector x has n rows.
Good.
Okay. So how can I express their product? What is A times n? A times x. Who has an idea? Okay, Alex. Yeah. You have an idea?
Is equal to 0, 0, 0, 0, 0.
Oh, what the? Jesus. We're not in the null space yet. This is actually, you just multiply them. A1 times x1 Boom.
I see.
plus A2 times x2. It's just dot product multiplication.
So why not equal to 0?
Because
Where is our B?
Oh, okay, well, yeah, B. But B doesn't have to be 0, B can be anything.
Oh, I see.
Yeah. I'm just choosing to expand out the left hand side.
Okay.
An xn. Okay. And I won't go through the hassle of writing this in sigma notation, whatever crap your professor does to confuse you. I'll try to keep things simple here. Okay, so I've done that. Now what do I do? Okay, so now that I've expanded this notation, 2 words should come to your mind. 2 words exactly. What are those 2 words? What does this expression look like? What does that expression look like? I just boxed it. What does it look like?
1x1 equals x2.
Yeah, but what does it seem like? What does it look like?
Oh, it's look like quadratic formula.
No, you've been
Linear formula. Linear.
you're
Ax plus b.
getting closer.
Y equal to X plus B?
No, linear combination.
Oh.
It's a linear combination.
Oh, it's a linear combination.
x1, x2, x3, all of those x's are scalars. You're multiplying a scalar by a vector, a1, a2, a3, and you're adding them up.
Which one is the scalar?
So, sorry,
A1 is the scalar.
yeah. So, these x's are scalars.
Oh, and
How do you know that?
A's are vectors.
A and the vector.
How do you know that?
How do you know that? I just memorized it. I don't know anything. No, because x, I told you, was a vector.
Right.
Every component of x has to be a scalar. Does that make sense? Because if you have a vector 1, 2, 3, I take each component. Each component is just a number. But if I take the components of a matrix, the components of a matrix are vectors. Because the atoms, you can kind of think of it as an atom, right? Okay, I've hit upon a good analogy. A matrix is like an atom, right? What are the components of an atom? The components of an atom are protons, which can be thought of as the vectors in a matrix. Okay, so hopefully that makes sense. So, this is the linear combination of the vectors a1, a2, all the way to an. Now, what mathematical word do I use to express a linear combination? Hint, it starts with an English alphabet letter.
Drum roll.
No, but what is it? How can I express the idea of linear combination?
Dot product.
No. Span.
Oh,
C-span. No, I'm joking. It's just span. So, what does that mean? That means what we've come to here, the column space. The column space can be simply thought of as the span of all these vectors of, a1, x1, a2, x2, a3, x3, all the way to an, xn. Okay, now we've simplified down the column space into a span expression. Now, how can I prove that the column space is an actual subspace that meets all three of these criteria? How can I prove that? Any ideas? Any ideas?
Yeah, what?
How can I prove that the column space is an actual vector space? Any ideas?
No.
Well, it's actually pretty easy. See, I just expressed the column space as a span, and I know that the span of any vector is gonna satisfy these three requirements. Why? Because what does the span tell you? The span tells you that the sum of the linear combination of any of these vectors are gonna be part of C of A. I've already got those two requirements checked off, right? Let me repeat that. Let's go through what we just did. Well, from the beginning, let's go from what we did. Our main goal was to understand how we could test if AX equals B has any solutions. That was our main goal, right? Who agrees with that? Right? What was our main goal?
AX equal to B.
AX equal B. We have to find the test, right? You have the horizontal line test to see if there is a function.
Right.
You have the column space to see if there is a B such that AX equals B, okay? And then what did we do? We said that C of A is, of course, an element of R1. In this case, it got pushed through a line. But then we said that C of A is the set. The column space is a set. What is a set? Who knows what a set is?
Set is a group of elements.
Yeah, so for example, if I take this water bottle, right? There's a set of atoms inside of it, which I will now drink. Okay, so hopefully that makes sense. The column subspace is a set of what? A set of all vectors B such that AX equals B. Right? Hopefully that makes sense so far.
Right.
And then we expanded A times X. We expanded A times X by just using the general notation of a matrix times a vector. And we got A1 x1, A2 x2, all the way to an xn, the sum of that. And then we recognized that this was a linear combination. And we understood that we could express our linear combination in terms of the span of these vectors. And finally, the final step of our proof that the column space is a vector subspace is simply to say that the span S of any set of vectors, is a subspace of Rn, right? And of course being whatever dimension these vectors are in. So automatically my three requirements for a space being a vector subspace are automatically qualified. Okay? So hopefully that made sense. Hopefully that gives you an intuition of what the column subspace is and why it's an actual subspace. So thank you for watching.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.